Neutrinos, the most mysterious particles in the universe. They move through all matter like ghosts, leaving almost no trace. Let's explore why they are so important. Since 1914, physicists have discovered a strange phenomenon. When the nucleus of an atom undergoes natural radioactive decay, a small portion of energy mysteriously disappears. Although this may seem insignificant, it violates the most fundamental law of energy conservation in physics. This puzzled the entire physics community at the time. To solve this problem, in 1930, an Austrian physicist proposed a hypothesis after extensive theoretical analysis. He suggested that beta decay not only produces electrons, but also gives rise to a type of particle that is extremely difficult to detect, carrying away a portion of energy, and this particle carries no electric charge. Therefore, it is considered a massless particle. Later, Enrico Fermi spent for years studying this strange idea by constructing a quantum field theory model. And after introducing it, he discovered that this particle was not only uncharged, but could also pass through atoms, as if it didn't exist. Hence, this particle was named the neutrino. At that time, both Fermi and Pauli agreed that, because neutrinos interact extremely weakly with matter, observing and verifying them became an impossible task. This led to neutrinos at that time existing only in theory. It wasn't until 1956 that American physicists Raines and Cowan indirectly detected neutrinos in a nuclear reactor, confirming that they are real particles. To better understand the nature of neutrinos, scientists began measuring neutrinos that reach Earth from space. Since nuclear fusion reactions also occur inside the Sun, American physicist Davis decided to detect neutrinos from the Sun. He placed a large amount of tetrachloroethylene solution at a depth of 1,500 meters in a mine. When the nucleus of chlorine-37 was struck by a solar neutrino, it transformed into argon-37. By measuring this, they could simply count the amount of argon-37 in the tank. From this, the number of neutrinos absorbed by the tank could be determined. According to theory, after excluding neutrinos from other cosmic sources, it was estimated that around 180 solar neutrinos could be detected each year. To obtain reliable data, Davis conducted this experiment over a span of 25 years. But surprisingly, the number of detected neutrinos was only one-third of the theoretical prediction. A significant portion of neutrinos remained unaccounted for. At times, they even considered modifying the theoretical model of the Sun. Later, through particle accelerators and devices like the Super Kamiokande, scientists discovered that neutrinos exist in three types known as flavors, including electron neutrinos, muon neutrinos, and tau neutrinos. And each type of neutrino also has a superposition of these three quantum states. They continuously oscillate between these three flavors, a phenomenon known as neutrino oscillation. According to quantum mechanics and particle physics theory, only particles with mass can change at different rates between different quantum states. This means that the mass of neutrinos is extremely small, but they are not completely massless. Moreover, according to special relativity, any object with mass cannot reach the speed of light. Therefore, even ghosts like neutrinos cannot exceed the speed of light. Subsequently, when quantum mechanics and special relativity were combined, the interactions of electrons, quarks, neutrinos, and 17 other particles were studied, formed the standard model of particle physics. Combined with the four fundamental forces of nature, it allowed the properties of neutrinos to be described more systematically. Thus, we know that, although neutrinos are one of the fundamental particles, they have no electric charge and have no electric charge. Therefore, they aren't affected by electromagnetic or strong force and only interact with the weak force and gravity. The problem is, due to the very limited range of the weak force and the mass of neutrinos, with their weak gravitational pull, this causes the influence of the weak force and gravity on neutrinos to be negligible. Therefore, neutrinos can pass through almost all matter, and no reactions occur. It can even pass through the entire Earth. Therefore, it is called the ghost particle. Moreover, The number of neutrinos in the universe is also extremely large. On average, every second, trillions of neutrinos pass through your body at nearly the speed of light. And these ghost particles were created 13.8 billion years ago at the birth of the universe, as well as throughout the evolution of the universe. It can be said that neutrinos are relics of the Big Bang. They not only carry information from the early universe, but are also the key to unlocking the mysteries of the cosmos. To capture these ghostly particles, countries around the world have employed various methods for indirect detection. For example, using deep Antarctic ice and Cherenkov detectors, detection using liquid scintillation, gas detection, ice detection, and various other methods. In China, a large spherical device, built 700 meters underground in Jiangmen. The device holds 20,000 tons of liquid scintillator. The mountains and rock layers act as natural filters, significantly reducing cosmic radiation intensity. When a large number of neutrinos pass through the detector, a very small fraction will interact with the liquid scintillator, producing faint flashes of light. These flashes are detected by photomultiplier tubes, allowing neutrinos to be directly captured. Through this, the mass hierarchy and precise oscillation parameters can be measured. Only when we sufficiently understand the fundamental particles that make up all matter will human civilization have greater hope. Neutrino research holds great significance in physics. It is the key to unlocking the mysteries of the universe. In the realm of fundamental physics research, we miss the opportunities with 17th century classical mechanics, 19th century electromagnetism, and 20th century relativity and quantum mechanics. But we must not miss the 21st century, with particle physics and neutrinos as representatives, becoming the key to reaching significant milestones in the progress of human scientific advancement. And don't forget to share your thoughts in the comments section below.